Okay, lads and ladies, welcome back to Calc 2. Let me get the office door closed here and we can get rocking and rolling. Today's going to be a fun day for us because we are almost done with the course. There is not a whole lot left to do. We've been working in polar coordinates, and today I'm going to work more with you on graphing curves in polar coordinates. And then we're going to start talking about the calculus operations that we can do in polar coordinates, some of which are definitely more exciting than others. So here we go. All right. So this is, as always, MAC2312. Section number 004, which means this is a Calc 2 class. And the date today is the 18th of April, 2022. We're going to do graphing. We're going to talk about tangent lines. Coordinates. And maybe introduce areas. And polar coordinates. But that last bullet point I'm not expecting to get to. That's really the final topic for the course. The real emphasis here today is on getting you comfortable graphing in polar coordinates. So we talked last week about how to go from Cartesian coordinates into polar coordinates, kind of one point at a time, right? If I give you the point, 2, 3, how do you find the polar coordinates for that point? Or if I give you the polar point, 5, pi over 6, how do you find the Cartesian coordinates for that point? That's all well and good, but what we really want to do is more like what we're doing at the end of the course last time, where you take a whole curve in Cartesian coordinates and translate that over into a whole curve in polar coordinates. That's the big boy game here. Once we can do that, you'll be at a place where you can start, sketching curves in polar coordinates with the sort of aptitude you have for, sketching parabolas and stuff like that. So let's get to it. Is there a problem with the microphone? Are you guys not able to hear me? Is the audio quality somehow poor? Do I need to fiddle with this? Can you hear okay? All right, let me know if the sound drops or if it's crackly or anything. I can fiddle with the audio settings. Okay, thank you guys. So, recall. The general procedure to sketch a curve in polar coordinates so R is some function of theta in polar coordinates. We first sketch in rectangular coordinates like the normal way, right? Where the vertical axis here is R and the horizontal axis here is theta. And then we transfer into polar coordinates. I like to think kind of one piece at a time. So maybe I have some portion of a polar curve that looks like, I don't know, something like this in rectangular coordinates, and I want to sketch that in polar coordinates. I would sort of do whatever, transfer that in here. What's this going to look like? Well, I haven't marked anything there, so it could really be just about anything. Transfer this in here sort of one piece at a time. Something like this is possible here. That's the vibe. So what I mean by one piece at a time is that like this portion of the rectangular graph would correspond to this portion of the polar graph. And today we're going to get a lot of practice at doing that, and taking kind of one chunk of this thing and seeing what chunk of this thing it produces. The example I've drawn here is actually a good one. We can begin with something like this. I think we did one of these last time. This shape down here is called a cardioid. Let's set up a specific example, get a specific rectangular graph, and see how we move that into polar. Okay, but this was the general procedure. I'm going to begin here, so for example, sketch a polar curve r equals, how about 1 plus sine theta. So I'm going to start with the rectangular coordinate sketch. And you always want to make sure you graph at least out to 2 pi. So this is my theta axis. This is my r axis. The period for this function, you want to know what the period is. Sine theta is periodic with period 2 pi. If you don't remember how to get the period or how to do any of these kind of wave graphs, you can look back at the announcements, sorry, not announcements, at the modules. And under the review material module at the very top here, under the algebra trig review, or you go straight to the trig review here, there's going to be a thing on graphing, right? Graphs of trig functions. And you can remind yourself how to graph all of these sort of things. So this is a regular sine wave, period 2 pi, that's been bumped up 1 unit. So I'm going to mark this as 1, and I'll mark this as 2. And I like to draw my equilibrium when you bump the thing up by 1, sort of the middle of the range comes up with you. I like to draw that in as a horizontal line. The other thing I like to do to try to guide myself here is to mark off a half period, which is pi, and a quarter period, which is pi over 2, and 3 pi over 2. So the amplitude for this, that's the number in front of the sine or cosine, that's going to be 1. The period is 2 pi, and it's been shifted up by 1. So there's a vertical shift up by 1 unit. So that means sine is going to start out here at the middle of its amplitude, or the middle of its range, right? You plug in 0 for theta, you get r equals 1 plus 0, which is 1. You know that sine reaches its max by pi over 2, comes back through its equilibrium at pi, reaches a min at 3 pi over 2, and finishes at its equilibrium over here. So here's my sine wave. This, right? Just a regular sine wave, only shifted up 1 unit. Then you take this and you transfer it into a polar coordinate graph. I showed you that polar graphing paper last time. You may find that stuff useful as you practice the homework problems, which ask you to sketch things. Remember, if WebAssign tells you to draw a graph, you need to practice drawing the graph. Do not look at the shit they have and guess. Don't copy one of the graphs down. Draw it on your own and then try to match your graph to one of theirs. It's the only way to develop the skill. The way we get the polar graph from the rectangular graph is by thinking about a little arm kind of rotating around. And this angle is your theta. And then how far out you're marking along the arm is your r. So we see from the rectangular graph that when theta is 0, r is 1. Mark this here as 1. So I'm starting right here. And as I rotate up, as theta increases, r is increasing. Mark this as 2. So as theta rotates up, this point is going to start to move out. And by the time we get to pi over 2, we're going to be out here at 2. So this is the polar point, 2 comma pi over 2. So I need to connect these 2 points with a smooth curve represented by this point kind of steadily marching outward. It's hard to do with the finger as theta sweeps from 0 to pi over 2. It's going to produce something like this. The line will always be perpendicular to these rays. That's a useful fact. So this portion of the curve comes from this portion of the rectangular graph. And watch, as I rotate this pen through, you'll see the intersection point with the pen marching outwards from distance 1 to distance 2. Here it goes, getting bigger, further and further out along the pen, further and further out along the pen till here. Now r is at its maximum, which is 2, and that's occurring when theta is pi over 2. So as I rotate past pi over 2, that point is going to start coming in along my pen. All right, so as I rotate past pi over 2, we're going to start coming in, coming in, coming in, coming in, coming in. And by the time we get to pi, we're going to be back to having radius 1. So here's the polar point, 1 comma pi. And we're going to trace something that looks like this. So watch this again. R is increasing, 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 increasing. R makes a max of 2. That's the furthest out along the pen we go. And then decreasing, decreasing, decreasing. That intersection point is coming in, always perpendicular to the pen. And then when we get to pi, we're back out at distance 1 from the origin. As I go past pi towards 3 pi over 2, r is starting to get smaller. And it's going to reach 0 when we get to 3 pi over 2. So if I were to come just a little bit past, like just a little bit past like this, r should start coming in. If I was to come a little bit past further, r should start coming in more. As I get to pi over 2, r is going to be 0. So we're going to sketch something like this. Something like this. In this region. And then as we rotate past 3 pi over 2, back around towards 2 pi, r is coming back up now, no longer 0, getting bigger and bigger and bigger, up to 1 again. So this is going to do this. And modulo my bad art, this is what the curve looks like. The point here, polar coordinates for this point are 0, 3 pi over 2. And the polar coordinates here were 1, 0 at the start and 1, 2 pi at the end. So this is our polar graph, and this is that shape we called a cardioid. Right? It kind of looks like a heart. It's upside down. Kind of looks like a booty, called a bootyoid if you want. But cardioid, heart shape, that's the technical term. And this is the procedure, right? Sketch the thing in rectangular coordinates and then kind of one piece at a time, you transfer the curve into the polar coordinate system. I have videos posted where you can see animations of this happening. I'd like to just expose you to that really quickly because I think they're very helpful. It's a hard thing to draw. This one's going to work. So, I think this one's a little better. So over here, you have the polar curve. Over here, you have the rectangular graph. So if r is constant, then as this arm rotates around, this never goes in or out, right? The distance you are out along this arm is your radius. That radius is constant. And you think of theta as just moving around. Here's cosine theta. Let me back that up just a little bit. All right, so we stop here. Here's the rectangular graph. This is good old cos theta. Watch as this point moves, what happens to the point on the arm here. This arm is like my pen. It's going to spin around. The distance we are out on this arm is your radius. Watch what happens as the radius becomes negative. Our first piece. Theta here is almost pi over 2. We're almost pointing straight up. We're almost to the x-intercept here for cosine. She knows pi over 2. And you see this point is coming in towards the origin as the radius gets close to 0. Now check this out. R is negative here. And normally, as theta is between pi over 2 and pi, we would be drawing over here in quadrant 2. But because the radius is negative, we have to reflect those points through the origin. That puts us down here. One more. So this is going to trace that curve twice as theta goes from 0 to 2 pi. I'll turn it off after this one. I just want to show you a nice animation of the motion I'm describing, because this is the way to think about stuff. Okay. Let's get back to the task at hand then, see if we can do some more of this stuff ourselves. Let's sketch r equals 1 plus 2 cos theta in polar coordinates. Same deal. First, we want to sketch this in rectangular Cartesian coordinates. Let me figure out, I'll draw a rectangular coordinate system. this. My period, t, is still 2 pi. My amplitude, a, is 2. And my vertical shift here is up 1. So let me mark off here like 1, 2, 3, and -1. Let me add in here my equilibrium line. It's shifted up 1. Let me mark a full period as 2 pi. The theta axis. That puts pi somewhere around here. Pi over 2 somewhere around here. 3 pi over 2 right here. So 2, 3, and negative. This is a cosine wave. You know, cosine starts at the top of its amplitude. So the period is always 2 pi divided by whatever number is in here multiplying the theta. So if this was like cos of 4 theta, this would be 2 pi over 4. If this was cos of 5 theta, this would be 2 pi over 5. The formula here is 2 pi over omega for sine theta or cos omega. I will try, but the trig review is where that stuff is all located, right? If you need to review how to find this stuff, then I would encourage you to look at the trig review module in Canvas. So cosine, remember, starts at the top of its amplitude. Here, that amplitude is 2, and we're shifted up 1. So this wave is going to start up here at 3. If you plug in 0 for theta, you get 1 plus 2 is 3. You know, cosine comes through its equilibrium at pi over 2, down to its min at pi, back through equilibrium at 3 pi over 2, and back up to its max at 2 pi. So the cosine wave here looks like this. More or less. And this is one period of the cosine function. Continues on, continues on. But I'm concerned with what's going on between 0 and 2 pi. So this is our rectangular graph. Now we're going to draw the polar graph. My radius goes up to a maximum of 3, so I should mark off like 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Maybe I'll use a different color. I'll try to not clutter the graph too badly. So use a different color for the graph itself. We start at the polar point 3, 0. And as this arm rotates up a little bit, theta is increasing, r is coming in a little bit. By the time we get to pi over 2, r should be at 1. Oh, before I do this, before I start plotting down here, one more thing. Marking off the maxes, the mins, and the equilibria are neat. Are there any other points in this rectangular graph that you think might be important as we try to translate into polar? When you look at this rectangular graph, are there any points on here that are significant or important in some way that are not yet labeled? So the min here of -1, that's at pi. I've got him, I'm happy with him. Well, yeah, maybe I want to know specifically when r is equal to 2. There's another value that I'd be much more concerned with, though. What kind of things do we always, yeah, we always want to find intercepts, right? And remember, in polar coordinates, when r is negative, you have to reflect the point through the origin. So knowing where r is negative and where r is positive, that's super important. I need to find these theta values. So we're going to solve the equation r equals 0. That means 1 plus 2 cos theta equals 0. And if you subtract the 1 and divide by 2, you get cos theta equals -1/2. And you can think about your unit circle. Where is cosine theta equal to -1/2? It's these points. So this is -1/2 comma √3/2, -1/2 -√3/2. Those angles then are 2 pi over 3 and 4 pi over 3. So this is 2 pi over 3, and this is 4 pi over 3. These two guys are so important that we're going to draw little rays in here as like guidelines. Remember the polar graphing paper had all of those rays emanating out from the origin? I'm going to draw in those little helper rays at 2 pi over 3 and 4 pi over 3. Those will be very helpful for us. Okay, now we're ready to go. So as theta rotates from 0 up to pi over 2, my radius is going from 3 all the way down to 1, which means I'm going to sketch something like this. Then as theta progresses from pi over 2 to 2 pi over 3, r is coming into 0. Well, if r is 0, then I'm at the origin. So that means I'm going to curl in like this. Now, as theta goes from 2 pi over 3 to pi, what's happening? Normally, I would be drawing over here between 2 pi over 3 and pi. That's this portion, these angles, these theta values. But r is negative here. So rather than drawing in this region, I'm going to be drawing in the reflected region over here. And specifically, what's going to happen? Well, we're going to poke out from the origin here. R is no longer going to be 0, but it's going to be negative. So I'll be somewhere over here. And then by the time theta gets to pi, by the time my arm has rotated all the way around like this, r is -1. So this is the polar point, -1, comma pi. So connect the dots. We're going to get something like this. Should be coming in perpendicular. As theta rotates past pi, r is coming back in towards 0, right? And we're going to get to 0 by the time we're at 4 pi over 3. So that means we're going to do this. And then as we rotate past 4 pi over 3, past this ray, r is positive again. When we get to 3 pi over 2, that's straight down. R is going to be 1. So here's the polar point 1, comma 3 pi over 2. This guy was 1, comma pi over 2. This is 1, comma 3 pi over 2. And then as theta progresses from 3 pi over 2 towards 2 pi, as my arm finishes this rotation around like this, we're going to run out to meet that point. Like this. And again, it is important to be able to match a part of the curve here to a part of the curve here. So let me just highlight one of these, the part that I'm highlighting in red here corresponds to the part that I'm highlighting in red here. When R is positive, these aren't too tricky, but curves where R is sometimes positive and sometimes negative, they're harder. If I shifted this sinusoid up higher so that this point came right up here, then we would have no portion of the curve where R is negative, which means we would have no inner loop, which means we would have just a regular cardioid. But with this graph dipping below the horizontal axis, we have a portion of the curve that is normally out here being reflected in here, and that's what creates the inner loop. There is a problem in your textbook, an example, not an exercise, but a worked example that I want you to read, where they discuss this. Here, example 11, starting on page 665. Investigate the family of polar curves given by 1 plus c sine theta. How does this change as c changes? These are called limosons. So here are some examples. What I would like you guys to do is for each of these, use Desmos or whatever to graph the rectangular curve and compare the rectangular curve for each of these. I'll show you how to do it to the polar curve that is given to you. My lab is just the best. So let's look at, I do this like this, is going to put it in polar. So I'll say y equals 1 plus c sine x. All right, and we can restrict our attention to the interval 0 less than x less than 2 pi. Now let's compare the Desmos graph over there to the polar graphs here. Shrink lens. So we'll say c goes negative 3 to 3. If c is positive 2.5, something like this, then you're above the horizontal axis, and then this piece below the horizontal axis induces this inner loop. If c is like 1.7, you still have a little piece below the horizontal here, you still have a little inner loop here. If I bring c down to 1, now the graph doesn't dip beneath the horizontal axis, it just kisses it, and that creates this cusp here. This is a cardioid. And if I make c smaller than 1, then my graph doesn't even touch the horizontal axis, and this thing starts to get softer and rounder looking. Right? When c is 0, that's just the function r equals 1, which in polar coordinates is a circle, and you get the idea. Right? So play around with this a little bit, and it will help you understand what's going on. But you need to develop this skill. You need to be remembering how to draw these graphs and learning how to transfer these graphs into these graphs. Are there any specific questions about how we got this limoson here? This is L-I-M-I-C-O-N. Any questions about how we got our polar graph here? Okay, let's try one more. Each of these that we've looked at is sort of representative of a family of graphs. We've looked at circles in the past. We've got a cardioid or two now, and that was our first lemma sum. This next one is called a pedal graph. So I want to sketch the curve r equals cosine 2 theta in polar coordinates. As we've been saying, first sketch it in rectangular coordinates. So here's theta, here's r. The amplitude here is 1. The period here, that period here is 2 pi. And there are no 2 pi over 2, which is just pi. Right? 2 pi divided by whatever this number is. There are no shifts. So I'll mark this as 1, this as -1. We'll call this 2 pi, which makes this pi, makes this pi over 2, 3 pi over 2. The quarter period here, pi over 4, 3 pi over 4, and so on. So this is a cosine wave. It's been squished in horizontally. It has a period of pi rather than 2 pi. We know cosine starts at the top of its amplitude. A full period here is pi, so a half period here is pi over 2. So it reaches a min. Its half period goes through equilibrium at the quarter periods and comes back up to its max at the full period. So there's one full period for this cosine wave, but I need to make sure I sketch it all the way out to 2 pi. So just copy paste this. Okay. Past pi, this would be 5 pi over 4. And this guy is going to be 7 pi over 4, halfway between 3 pi over 2 and 2 pi. So there's your rectangular graph. Let's look at the polar graph. I'll mark this as 1. And I'm going to add in some helper lines here as well, right? These places where we have r equals 0, which are the multiples of pi over 4. And to add those in as helper lines. So pi over 4, 3 pi over 4. 5 pi over 4. 7 pi over 4. All right. Now, this point, theta is 0, r is 1, is going to come to this point. Theta is 0, r is 1. Over this portion of the graph, from theta equals 0 to pi over 4, r is retreating towards the origin, So by the time my arm rotates up to here, right, as we go from here to here, my point needs to come in to the origin to have r equals 0 when theta is pi over 4. So that is going to give me a piece that looks like this. When r is 0, I'm out here at 1. When r is a little bit bigger, when theta is a little bit bigger, r is getting smaller. As theta rotates towards pi over 4, r is going to 0. When theta is pi over 4, r is exactly 0. Next, r is going to become negative. So as I rotate past pi over 4 towards pi over 2, normally I would be drawing up here, but r is negative. So that means I'm going to be drawing over here. This is like your negative polar axis. And what's happening? Well, r is going from 0 out to a max of -1. That means I'm going to be running down here from 0 out to a max of 1 as this rotates from pi over 4 to pi over 2. We'll create something like this. Right here, this is the polar point, -1, comma, pi over 2. As my little arm rotates past pi over 2 towards 3 pi over 4 here, r is still negative. So rather than drawing up here, I'm going to be drawing over here. And what's going to happen is that as theta rotates through this region, r is going to be retreating back into the origin, right? R is retreating back into the origin. So I'm going to create a shape like this. So I'm hitting the origin for a second time. I came in, boom, around, boom. First origin hit, second origin hit. As theta rotates past 5 pi over 4 towards pi, that's this region, r is positive, so I don't have to worry about reflecting. We're going to poke out of the origin a little bit, and then by the time we get to pi, we need to be all the way out at 1. So here's the polar point 1, comma, pi. This is going to produce this. As theta rotates past pi towards 5 pi over 4, that means I'm working in here. R is running back in from 1 to 0. And by the time my little arm gets to 5 pi over 4, I need to be back into the origin. From 5 pi over 4 to 3 pi over 2, r is negative. Normally, if r were positive, I would be drawing down here. But because r is negative, I'll be drawing in the reflected region over here. Again, you can kind of think of it like this. So as I come just past 5 pi over 4, normally I would be drawing over here. But because r is negative, I'll be drawing over here. And what's going on? Well, the same thing. R is running from 0 out to 1. It's negative though, so rather than running 0 out to 1 like this, we're running out like this. This is 1. And we're going to get here. This would be the polar point, -1, comma, 3 pi over 2. So that portion of the graph here produces this portion of the graph here. As we rotate past 3 pi over 2 towards 7 pi over 4 through here, r is negative, so we're drawing in this reflected region over here, and it's retreating back to the origin again, like this. And then finally, as we go past 7 pi over 4 towards 2 pi, r is poking its way back out in a positive fashion again. So this is the shape we get. These petals should all be symmetric. My art is not perfect, but you get the idea. And as I mentioned, these are called petal graphs. So these come in the form r equals some constant times cos n theta, or r equals some constant times the sine of n theta. And I would like for you to experiment a little bit. I have a question. How is n related to the number of petals? So for example, here, this was the polar curve, r equals cos 2 theta, and we have 4 petals. The A is just like the amplitude, right? It tells you how big each petal is. The N is what tells you the number of petals. The answer is not quite as obvious as it might seem from this example, but it's very close to that. So I can show you a couple more examples in Desmos really quickly. Desmos does have a polar mode. You can change it like this. And then if you type r as a function of theta, it will graph in polar. So here's the one I just did, r equals cos 2 theta. Right. Petal graph, 4 petals. If I were to do cos 4 theta, 8 petals. Cos 6 theta, 12 petals. No, cos 3 theta. Oh, that's 3 petals. Cos 5 theta, it's 5 petals. Cos n theta here, I'll just leave it like this. We should have this being integers. So from 1 to 10, steps up to 1. Yeah, so integers. Something kind of neat happens. And sine n theta does the same thing, but slightly different looking. Turn one of these off, just look one at a time. Next. Maybe I'll put an A for each of these. It's down here. And you can see how changing the coefficient in front changes things as well. I'll go ahead and save this one and post link. I'll post that in your modules under the polar coordinate stuff. You can play with this. Okay. Again, let's try highlighting a portion here that's not super obvious where it comes from. Maybe I could ask you, this part of the graph in rectangular coordinates gives me what part of the graph in polar coordinates? What quadrant? Quadrant 1, 2, 3, or 4 does this part of the graph end up in? Is the question clear? The red shaded part of the graph here is going to give me some part of the curve down here. I want to start by asking which quadrant, 1, 2, 3, or 4, does this part of the graph land in? I have one correct answer in the DMs. So the way we would normally think about this is that 5 pi over 4 is right here, right? 3 pi over 2 is right here. So the region from 5 pi over 4 to 3 pi over 2 is this region, which is a part of quadrant 3. But r is negative here. So instead of drawing in this region, we'll be drawing in the reflected region up here. The part of the graph that corresponds to that red highlight portion there is this. This is a skill that's going to be very important when we talk about areas in polar coordinates, because I'll ask you, set up an integral that gives me the area of this loop. And you might think you're going to integrate from pi over 4 to 3 pi over 4, because that's what it looks like. But that's not correct. Right? This part comes from 5 pi over 4 to 3 pi over 2. And it's not always obvious, right? Just looking at this picture, it's not obvious. You need to think about this graph being transformed into this graph. All right. I want to summarize and tell you a little bit what you're responsible for. What do I require you to do? You are required to know the following polar graphs. Right. So just like how in your algebra classes, you have to know what lines look like, the equation of a line. You have to know what parabolas look like. You have to be able to find the equation of a parabola. You have to know what circles look like. You have to find the equation of a circle. In polar coordinates, I expect you to know circles, either centered at the origin or along the axes. Right, so stuff like this or this or this. This is like r equals a constant. This is like r equals cos theta, and this is like r equals sine theta. And there are some modifiers you can apply to those, but these are just examples. Circles, you got to know your circles. I expect you to know cardioids. These are things like this. So again, for example, something like r equals 1 plus sine theta, or this would be something like r equals 2 plus 2 cos theta. I want you to know your circles, and I want you to know your cardioids. Limaisons. These are like cardioids, but with inner loops. So the same sort of bullshit. Stuff like this, which might be something like r equals, what do we do? 1 plus 2 sine theta, or r equals 1 plus 3 cos theta, something like this. Stuff along these lines. And then finally your petal graphs. And those end up looking like we saw. This sort of stuff. The sine ones are offset a little bit. So they look like, okay, spins down. They look like r equals plus 2 thetas would be r equals sine of 3 theta or something like that. So these are the basic families, right? Circles, I think, are fairly obvious. We saw those as kind of preliminary examples. So the new ones, the ones we need to be practicing between now and the final, would be cardioids, limaçons, and petal graphs. Questions on how to sketch these things, right? How to go through that procedure. If I give you the equation, how can you come up with a polar graph? Okay. Then in these last few minutes of class, what I want to do is show you tangents in polar coordinates. It's true that sine 5 theta would have 5 petals, yeah. Sine 6 theta would have 12. Sine 7 theta would have 7. So we know that the slope of a tangent line comes from the regular old-fashioned derivative dy dx. It's not quite that simple. So Fabrice, that's a good guess. It's not the case that sine always gives you the n petals and cosine always gives you 2n petals. It's a little different. But if you experiment, right, just experiment with it, you will discover the pattern very quickly. So let's get back to here. So the slope of a tangent line we know comes from dy dx, right? That's something we've known since Calc 1. In polar coordinates, x is r times the cosine of theta, and y is r times the sine of theta. So if r equals r of theta is a function of theta, then we can get parametric equations for a polar function. By plugging in r of theta for r here. So I would say x of theta is r of theta times cos theta, and y of theta would be r of theta times sine theta, right? R of theta is like the curves we were looking at a second ago. R of theta equals whatever, sine 2 theta. You take that function for r and you plug it into these equations that tell you how to go back and forth from Cartesian to polar. R isn't a constant here, it is a function that changes as theta changes. So in here goes r of theta, and you get this. This is x of theta. I'm saying x is a function of theta. You could just write x equals if you want. But the big deal is that these are parametric equations. And we know how to find dy dx for parametric equations. Try it. If you take the polar curve, let me try to convince you this is true really quick because we're doing okay on time here. If I take the polar curve, r equals 3, here it is, and I plug that into my parametric equations, and I get x equals 3 cos theta. So I'll write 3 cos t, and y equals 3 sine theta. I'll write 3 sine t, and I'll say t runs from 0 to 2 pi. And the green and the blue are identical, aren't they? What if I try something else, like r equals 1 plus sine theta? Here's that guy in polar coordinates, right? Normal polar graph stuff. If I write 1 plus, so sine theta, or sine t, sorry, t here, and 1 plus sine t here. It's so fucking slow. Jesus Christ. Then again, same thing. So every polar curve, like r equals r of theta, can be written in parametric form by plugging the r's into these equations that we got on the first day talking about polar coordinates. And that gives you parametric equations. Thus, from section 10.2, we know that dy dx should be dy d the parameter, so dy d theta, divided by dx d theta. So we need to figure out what is dy d theta and what is dx d theta. And the trick again is to come back here. So if you take this guy and you differentiate with respect to theta, you'll see that dy d theta is a product rule thing. You have to differentiate r of theta times sine theta. So that would be dr d theta times sine theta plus r of theta times the derivative of sine theta, which is cos theta. And similarly from the first one, you can get dx d theta. Again, product rule, this is going to be dr d theta times cos theta plus r times the derivative of cos theta, which is negative sine theta. So this is going to be minus r of theta times sine theta. So if I take those and I plug them in to the recipe we get from thinking about these as parametric equations, dy d theta upstairs, so I have a big fraction. The numerator here, dy d theta, is dr d theta times sine theta plus r of theta times cos theta. Dy d theta. And the bottom, dx d theta, is dr d theta times cos theta minus r of theta times sine theta. This is your recipe for dy dx, or the slope of the tangent line, in polar coordinates. Now you have to plug in the theta value that you're looking for. So let's do this. Let's do this for one of the curves we were playing with. We graphed, what was the last one we actually sketched out ourselves? Petal graph. Let's do a cardioid. We sketched 1 plus 2 cos theta. Let's find one of the tangents to that guy. I'll hold here for a minute. Anybody's writing? And then we're going to do the calculation. So this is the blue box statement that you need to remember. Here we go. Let's find the tangent, or find the slope of the tangent line. We'll just say to the curve r equals 1 plus 2 cos theta at the point where theta is pi over 3. This is a curve we we graphed a little bit ago. 1 plus cos 2 theta. This was the limison looking like this. And the point where theta is pi over 3 is right here. So I'm looking for the tangent line. As I've drawn it here, it looks like it might be horizontal. It's hard to say exactly what it is. I'll just sketch it like this. We want this tangent slope. And we know that the tangent slope always comes from dy dx evaluated, in this case at pi over 3, at whatever you plug in for the variable, the value that puts you at the point you want. And we just discovered that dy dx should be dr d theta times sine theta plus r of theta times cos theta divided by dr d theta times cos theta minus r of theta times sine theta. Here, for this curve, dr d theta, that's what you get when you differentiate this r function with respect to the variable theta. So the 1 differentiates to 0, and 2 cos theta differentiates to negative 2 sine theta. So dy dx is negative 2 sine theta times sine theta plus r of theta is 1 plus 2 cos theta times cos theta, all divided by dr d theta, which is again negative 2 sine theta times cos theta. I'm just plugging into this formula, minus 1 plus 2 cos theta and sine theta. And how much you want to simplify this, totally up to you. I'm just after the number. I want to know the slope of this line. And I'm going to get it by plugging pi over 3 into this expression. I'm not even going to bother simplifying. I'll just write it out. So the slope of the tangent line is dy dx evaluated at theta equals pi over 3. So what is this? Well, the sine of pi over 3 is the square root of 3 over 2. All right, so the cos of pi over 3 is 1/2. So I'm going to be plugging in root 3 over 2, root 3 over 2, 1/2, 1/2, root 3 over 2, 1/2, root 3 over 2. What is that? That's negative 2 times sine theta, which is root 3 over 2 times sine theta, root 3 over 2, plus parentheses 1 plus 2 cos theta. So that's 1 plus 2 times cos of pi over 3 is 1/2. All times cos of pi over 3, which is 1/2. Divided by negative 2 times sine theta times cos theta. That's negative 2 times sine pi over 3 root 2 times cos of pi over 3 minus parentheses 1 plus 2 times cos of pi over 3 is 1/2 times the sine of pi over 3. It's messy, sure, but fuck it, we can deal with it. It's not that bad. We're Calc 2 students. You guys made it all the way through Calc 2. This is the end. You can do arithmetic. Root 3 times root 3 is 3. You can cancel one of these 2's, and you get negative 3/2. This first piece. Plus 2 times 1/2 here. This is 1. 1 plus 1 is 2. So this whole piece here is 2. Two times 1/2 is 1. Downstairs. 2 times root 3 over 2 times 1/2. That's just square root of 3 over 2. Cancel 1 and 2. You've got a negative there, so this piece is negative square root of 3 over 2. This piece is also a 2. Same as the piece of 3 over 2. All right. So the numerator, negative 3 halves plus 1, that's negative 1/2. The denominator is negative root 3 over 2 minus 2 root 3 over 2. That's negative 3 root 3 over 2. This. Flip and multiply. And you're going to get 1 over 3 square roots of 3. That's it. So this blue line up here, it looked like it might have had a slope of 0, a horizontal slope, but not quite, right? It's a very, very small positive slope. Okay, this is where I'm going to end for today. On Wednesday, we're going to talk about areas in polar coordinates. We'll talk a little bit about arc length also. I want to leave you with some information on exam 3. First, exam 3 is going to cover everything from exam 2 to now, right? So power series, it's 11.8, 11.9, 11.10. Parametric equations, 10.1 and 10.2. And the very beginning of polar coordinates. What we've been doing here, tangent lines, not on exam 3. That stuff will be on the final, but not on exam 3. So for exam 3, you've got all of the power series stuff. Then all of the parametric equation stuff. So graphing parametric curves, finding tangents, areas, arc lengths with parametric curves, all of that. And then the very basics of polar coordinates. So like I give you a point in Cartesian form, can you give me some polar coordinates for that point? I give you a point in polar form, can you give me the Cartesian coordinates for that point? That sort of stuff. So the majority of the test here is going to be power series and parametric curves. That should be your focus. The polar stuff that has to do with calculus that we just did here, that will only be on the final. So as far as polar stuff is going, just transferring points back and forth one at a time, some basic graphing, but no calculus in polar coordinates. What do we mean by the same thing? I don't have a practice test for exam 3. That's not something I prepared. So I make that for exam 2 because of spring break. And I don't have one. So I can't promise that I'll send something like that out. I can try, see if I can find some time, but I can't make any promises. I'm quite busy now. Yeah, sorry. But work the study guide problems, right? If there's something that you're uncertain about, bring it by my office hours. The other thing I can recommend, those problems in my practice test, just like the problems in my actual tests, are very similar to the review problems in the book. What is a parametric curve? How do you sketch it? How do you find the slope of the tangent? How do you find the area? How do you find arc length? What does polar point mean? Like this shit, right? Problems 1 through 5 here in the concept check. Problems 1, 3, 4, 5 in the true false. And then the exercises for chapter 11 review, any of 1 through 4, any of 5 through 16, 17, 18, 37 through 40, right? Look at the chapter review. Look at the chapter review for chapter 10. Just skip anything that has to do with 10.5 or 10.6. And for chapter 11, right? And pay special attention to the stuff that's related to power series. This is the best way to prepare. So the study guide is good. Definitely do the study guide. And then if you're looking for extra practice, I'm sorry, I don't have a practice test for test 3, but look at the chapter reviews, chapter 10 and 11. That will be more than sufficient, I think. Any other burning questions or comments, anything you'd like to ask before I let us go? Alrighty, then I'm gonna go ahead and sign off here. You guys work hard, get ready for the test, and I will see you on Wednesday.